Hey folks, I'm teaching a class this semester called Spacecraft Design, which has been very fun for me, and the textbook I'm using is called Space Vehicle Design. It's a book that's relatively old at this point, and you can get it from Google pretty easily just by Googling it. Anyway, I'm teaching chapter 6 right now called Atmospheric Entry, which is all about coming into the surface of the planet. So, you were, say on a a circular orbit, and you're coming into the atmosphere, and you've got your velocity vector, your flight path angle, you've got your range value s, your altitude above the surface, r is the radius of the planet, and then little r is you can look at it here, basically like big R plus H. Big R plus H is little r, and I think that's it. Yeah. We got lift on here, you got drag on here, and for this case we are going to do what's called the ballistic entry. And for the ballistic entry, we're going to assume that zero lift, you can't see that, let me move myself out of the way. There's zero lift on the spacecraft, okay? And so if you make a lot of these assumptions, the book kind of goes through this example here, and you get this analytic equation here. Oh, that was kind of wild. You get this analytic equation here, and so VE is the entry velocity, beta is a density term, rho S is the density at sea level, gamma E is the entry flight path angle, S is the planform area of the spacecraft, CD is the drag coefficient, M is the mass, and then I already said beta, and then H is the altitude above the ground. If you scroll all the way, so this is an analytic equation that relates altitude to velocity. And if you scroll all the way to the problems, if you scroll all the way here to the problems, problem 1 says that the Mercury spacecraft was designed to perform a ballistic reentry with the initial conditions, yada, yada, yada. And so here's the mass, the drag coefficient, the area, the relative to the air entry velocity, RE, which you obviously know I'm going to write some Python code, so that's one thing that I haven't put in here, was RE is 6378000, and then all of this is good. G is 9.8. Yep, I already put beta in there. And so the idea is that if the maximum design reentry deceleration was to be 8 Gs, what was the desired flight path angle for the Mercury spacecraft? Well, if you go back to these equations here, basically what you can do, or not these equations, sorry, if you go back to that analytic equation, this one here, you can actually just program this pretty easily. So I put the altitude above the ground of 0 to 122 kilometers. Here's the radius of Earth in meters. Here's the entry velocity. Here's that beta constant, which is a density parameter. Rho at sea level, mass of the spacecraft, drag coefficient, area, flight path angle. And then this is actually, this needs to be gamma E, the entry flight path angle, and this needs to be gamma E. Here is the really complicated equation. I import numpy and matplotlib so I can use the exponents. And then I can plot just velocity pretty easily, but somebody said, how do we get acceleration? And I looked at these equations and I said, well, dh dt, if we're falling ballistically, we could get dh dt here, which is dr dt, and if we have an equation of v as a function of altitude, so I said, okay, well, if we take a first order derivative of this equation and get dv dh, if we do dv dh times dh dt, that'll be dv dt, and dv dt is acceleration. And I did this, and I ran with it, and it says I forgot to change gamma somewhere else here. If you run this, you get these two plots here. H is not defined. Where? Line, oh, okay, when I plot, here we go, H A, and then H A, and then V, I I changed all my variable names right before this video, and of course Excel A for analytic. Oh, Excel, oh, capital. Oh, why would I do that? I'm just going to do a lowercase a. Okay, sorry about that. So you get these plots here, and so you have to look at it from right to left. So the velocity at altitude is high, and then it starts coming into the atmosphere, and then it loses velocity until it comes in and hits the ground. And then over here, using my first order derivative to get dvh, and then using the equation from the book to get dr dt, which dr dt is equal to dh dt, and then doing a first order derivative to get dvdh. You can multiply those two together to get acceleration, and then I divided by 9.81 to get g's. Here are the g's that the spacecraft experiences. Now, one of my students in class said, well, how long would that take? Well, unfortunately, because we have dh dt, so we could integrate dh dt as a function of time and using a given time step and figure out how long it is. The problem I have is that this equation is an approximation, and then this equation here assumes that gamma is constant. And if you go to these equations here, you see that d gamma dt is not constant. It changes. And because of that, this is an approximation, and then this is a first order derivative, which means that's also an approximation. And so I didn't like all of these approximations, so I didn't want to do one more and say, okay, let's just integrate dh dt and get altitude as a function of time. I said, you know what, why don't we just create a derivatives routine where we have t and state, and let's just create a function that can handle all of the states. So I'm going to put this over here so you can see it, and then this over here, and let's just code up these equations. So let's do the first one. So dv dt is negative d over m minus g times sine gamma. Let's see, d gamma dt is, so L is 0, but I'm going to leave it in there, L minus g minus v squared over r times cosine gamma. And then let's see, ds dt, which I really don't care about, so I'm going to leave it off. And then I'm going to do dh dt. Well, let's do dr dt. That's fine. So h is equal to all. Interesting. Let's keep track of h. So we're going to do dh dt. We'll keep track of h. I'm going to do v times np sine gamma. And then L. So now we have to come up here. And so L is 0. D is 1/2 rho v squared times s times cd. And then little g is g at sea level times r over r plus h, all of that squared. Okay, so what don't we have? So let's see, L is 0, so we need rho. So rho, there's an equation for rho, and that is here. So rho is equal to rho at sea level times np.exp of negative beta times h. Okay, so that's rho. And then v is an input, so we need to make our state vector. So state vector. So I'm going to make v state of 0. I need h, I'm going to make it state of 1. I'm going to make gamma state of 2, and then I think that's everything that I need in terms of states. So we need to grab these constants. So here's r. I could probably make those globals, but to change re to just r. And then I think I can get rid of this, by the way, so I can just code. Let's see. Okay, so there's a state vector. Here's my density model. Here's my aerodynamic model, and then I guess this is my gravity model. Do I have gravity at sea level? I don't, right? So gravity at sea level is 9.81. And then I have drag, we're good. M is up here. Hopefully it can grab M. And gamma is an input, G is from there, a little r. Okay, so in the gravity model, little r is big R plus h. And big R is a constant, h is a state, and then gamma is a state, dh dt. Okay, so then what we need to do is then, so these are our dynamics, and then we need to return state dot. And so state dot is np dot as array, and then it's going to be dv dt, dh dt, and then d gamma dt. So dv dt, dh dt, and then d gamma dt. And I think I got my d gamma dt equation wrong, because I just remembered that you have to divide by v. Yeah. So where is that? So here you need to divide by v. I feel like this is going to blow up because if v is 0, we're going to have to put some checks in here. Same with h. Like if h is less than 0, we need to stop. But for now, let's just see if we can integrate this. So this is my derivatives function. So now we integrate with ODInt. So I need to make my initial conditions. So state initial is np.asArray v0, h0, and gamma 0. But it's not v0, it's the entry velocity, which I think I have defined up here. And then it's my entry altitude, which I don't have defined, but I will define it. So that's, so I'm going to put HE here, and then say HE is 122,000. That's my entry altitude. Okay. Let's see, and then I need gamma E, and I think I have gamma E. Yep, I do. We're good. Okay, so then I can integrate, so I can say T-out is np.linspace, and I guess I'll just simulate for 100 seconds, and then I'll say T-out, state out is I.ODInt, and you might be wondering what I is import scipy.integrate as I named it that. So I think I'm going to call it sci, just to make it easier, so that'll be sci for scipy. And then you have to give it the derivatives function, you have to give it the initial conditions, and then the output, the T output vector. So let's see if that runs. So state with an E. Let's see, float object is not subscriptable. Okay, so let's go, I could go Google this, but let's try state comma T. No, that's not right, so it's T comma state. And what is the error that it's giving me? V of state 0, state initial. Yeah, what's state initial? It's an array, okay. So what we can do is we can just open some codes. So it's, yeah, okay, so it is state comma T, so I actually had that backwards. So what I did was I just opened up an old code. So it is state comma T. Okay. So then why did it throw an error now? It said the size of the array does not match. Now why is that? So how do you call, so it's derivatives initial T out. Okay. So 1, 2, 3, yeah, that's the, oh, duh. I have to return state dot. Okay. So there we go. Oh, too many values to unpack. So when you run, okay, so you don't get T out, you just get state out. Okay, there we go. Okay, so that ran. So then if I look at my variables over here, let's see, there's state out. Okay, you can hardly see that. So np.shape of state out is a 1000 by 3. So if I want v numerical, that's state out of all, comma, the first column, and then h numerical is state out of all, comma 1, and then gamma numerical is state out of all, comma 2. Now what's interesting, by the way, is as I was reading this in the ballistic trajectory, is they assume that that gamma is actually constant. And so what I'm curious first is so here I'm plotting the analytic variables. I'm going to put plt figure plt dot plot, and I'm going to plot t out comma gamma numerical, and then do plt x label flight path angle in radians, and then plt dot y label. Oops, I was wrong. This is the y label, and then the x label is time, and then plt dot grid. So let's run that. I'm curious if the flight path angle is constant. And so, well, I only simulated for 100 seconds, so let's not, I don't know if this approximation is still valid. What I want to do is I want to plot, so I want to do a label and plot the analytic, and then do plt.plot h numerical, v numerical, and do label numerical, and then do a plt.legend, okay? And then do the same thing here, except, ooh, wait, I gotta take, so I don't actually know what the acceleration is, so I do need to do a derivative, so I need to say, like, excel numerical is v numerical, and then I'm just gonna copy this line of code here, except since I'm doing it with respect to time, I can do vnum, and then I can just go ahead and do t out and t out, and then that way that's dv dt right there. I don't have to do the chain rule, and then I can plot here plt.plot hnum 0 minus 2, and then excel num over 9.81, and then again do a label analytic, and then down here do a label numerical, and let's see, t out's not defined here, t out, okay, and then let's see, so there's the numerical, so they look, you know, that doesn't look right at all. It's like gaining velocity because gravity is pulling it in. Okay, but it does look like it is rolling off, and the G's are starting to get different. So let's keep simulating. So I only simulated for 100 seconds. So let's do 1,000 seconds, and let's see what happens. Oh, interesante. Look at that, man. That's totally different. That's crazy. And then look at that flight path angle. And that's 90, right? Yes, that makes sense. I mean, it's coming in at 2, and then it slowly turns and goes down to 90. So and this is numerical. Let me plot in orange. So, oh yeah, I forgot to throw the legend on this guy. So plt.legend. And then this guy, let me plot this guy in orange, so that you can compare apples to oranges. So, okay. Shoot, what color is that? It's not magenta. What? That's orange, isn't it? Okay, I'm just gonna leave it. This is pretty close, which is cool, but this is not. So here's another thing that I wanted to try is that down here, the max acceleration is equal to negative parentheses beta VE squared over 2E sine gamma E. So what I'm curious is, which was more accurate, the analytic or the numeric? And so what I'm going to do is down here, let's see, in the analytic equation, I'm going to do A max is negative beta VE squared over 2, and then E? Is that literally like 2.71818? I guess so. Can I just do like NP EXP of 1? It's probably fine. Times NP sine of gamma E. Right? Gamma E. Okay, and then I'm going to print max excel equals A max, and then say max G equals A max over 9.81. Okay, so it's saying that 5, but see, how do I know, like, where did that, shoot, what am I looking for here? I mean, like, this probably came from that analytic equation with all of those assumptions. So I don't know. But then again, like, I believe this more. Like, this, saying the flight path angle is constant is kind of ridiculous. That's my vote anyway. But let's get rid of the elephant in the room. How long does it take to hit the ground, right? Let's plot altitude as a function of time. That's the kicker here. plt.figure, plt.plot,tout, h noon, plt.xlabel, time, plt.ylabel, altitude, meters, plt.grid. What's your vote? What do you think? How long did I simulate for? 1,000 seconds? I'm saying 4 minutes, which is 240 seconds. Drum roll. No, I was so wrong. 450 seconds. Yeah, right here. So 450 seconds. So right at here, so we only need to simulate for 450 seconds. So let's go back and let's change this to 450 here, 450, and run that. Okay, so there's, yeah, so that makes sense. So both equations end at the same point now. And then that looks pretty cool still. And then there's a flight path angle going down, like it's like comes in at -2 degrees and then goes down to -90. And then there's your altitude as a function of time. So here's like your max Q area. And then down to there, down to 450. So 450 divided by 60 is what, like 8 minutes? 450 over 60. Yeah, like 7.5 minutes. So I was trying to base it off of like how long, like, you know, the SpaceX launches take and things like that. So that's what I was going for. Cool. I think I did everything I wanted to do. I answered my student's question. It takes 7.5 minutes to land, and I also taught my YouTube followers how to integrate a multi-degree of freedom system in Python. So hopefully you enjoyed this video, and if you have more questions, post in the comments.